Hello, this is Nitin Dahad with the Times. I'm speaking today to Russ Garcia, who's the CEO of a company called Menlo Micro. Russ, hello.
Hello, Nitin. I really appreciate the time.
Thank you.
Good to see you.
Russ, tell me, we haven't really covered Menlo Micro in depth. Tell us what is Menlo Micro? What do you do?
So we make a device called the Ideal Switch, and it's basically a device that transfers energy far more efficiently than any other device. It's being used in high frequency systems all the way to energy distribution systems.
Okay, that's the marketing. Now, what does that mean? What's an ideal switch?
An ideal switch. So a perfect switch would mean that I had zero contact resistance when it's on. I have infinite contact resistance when it's off.
Right.
I guess it would be free.
Okay. Okay. But
The ideal switch is as close to zero as you can. So this is basically about Ohm's law. I'm a conductor, not a semiconductor. So I'm linear over a very wide frequency range and up to very high millimeter wave frequencies. But at the same time, I am able to transfer energy because I scale so well. I can put many of these in parallel to transfer energy.
Tell us a little bit about what the innovation is, what you're doing. Why would our readers care?
So the innovation is it is a MEMS-based device, and your readers that have looked at MEMS over the years, the promise for a metal contact switch because of Ohm's law and the linearity properties and the current density properties you could get from that has been a brass ring for a long time. There was a number of companies that tried to do this 20 years ago. Virtually all failed. They failed two reasons, because not only is it the technology that's important, it's the scaling that's important. And to scale these things, you need to put them in a semiconductor fab. Well, semiconductor fabs have two kinds of materials. They have pure metals, which are not very reliable. Doesn't take long to bend a gold wire to break it. And secondly, is silicon dioxide is not a conductor. So what happened was GE really set out to.
You mentioned GE. Just go back to what's the GE connection?
Okay, so the GE connection is this actually started in GE. GE's original concept, early 2000s, was to use MEMS to reinvent GE's founder's invention, Thomas Edison's invention, the circuit breaker. Okay. And they actually intended to go source all of this capability from one of the many companies that were trying to do this. They were never able to get something that was reliable enough. So subsequently, they took it inside to GE Schenectady. Simple enough, they took they realized the material science was actually the issue. So they took the metallurgists that do the metallurgy for the fins on aircraft engines, combined them with the device physicists, and they basically developed a very reliable metal alloy that has very high current density capabilities, and that was the start of the ability to make this kind of MEMS.
So that's culminated in some kind of product in 2015, and then you spun out in 2016. Is that right?
Yeah, as a matter of fact, GE used it originally in MRI machines. So okay. They built some inside. Were able to prove that they could handle lots of power at high frequencies, which was perfect for MRI. I met the founders, the co-founders of the company in 2015. We basically put together a plan with GE Ventures to spin the technology out, and the company became real and raised our first money in December of 2016.
Talking of money, I think you've raised about $238 million so far. Yeah. And you said about 70 people.
We have about 70 people.
Okay. Yeah. And you're doing revenue. I think you're close to selling your millionth switch. Is that right? We should be within the next 3 months. We should have sold our millionth switch. So what do you put the success down to? What is the what are the things that customers have said, okay, well, maybe we need to look at this and maybe utilize this?
Well, there's certain things that you just can't do with any other technology. One is to be able to have a scalable electromechanical or conductor is really critical in a number of things. Being able to be linear from DC to millimeter wave, everything from in an RF system, beamformers and those kinds of things, to actually what's driving our initial revenue, which is test and measurement, believe it or not. As if you look at an AI device, a GPU, high-speed serial interfaces like PCIe Gen 6 require very, very high-speed switches to be able to test them from DC all the way up to their at speed. And so that's become a really, really fantastic starting business for us.
And so, yes, I mean, that leads us, there's three key areas. I think AI is the one that's driving your revenue right now.
Yes.
The GPUs predominantly, and the testing of those. So that's at the packaged device stage, right, mostly.
Mostly the packaged device stage, although we're moving into the probe stage as well.
Okay.
And we expect that business to continue to grow at a really high rate over the next several years.
And then the other two areas, I think you're sort of just getting into aerospace and defense and also energy distribution. Just tell us why those areas as well.
So aerospace and defense ends up being a pretty interesting area because it's a great place to develop things. So I mentioned beamformers just a minute ago. So satellite communications advancements a lot of times will happen in aerospace and defense, but the leverage back into commercial communication infrastructure becomes really key there, and so that's one place. The second area is even our power devices are starting in aerospace and defense systems, but then will leverage back out into the commercial markets as they're developed.
And energy was the other area.
Yeah, energy was the other area. We announced something just a few months ago.
The micronuclear reactor, and I think you tell me why that was used there.
So that's an interesting story. So the micronuclear, the Defense Innovation Unit, which was funding a contract for the Navy. Mm-hmm. Navy happens to be the world's most advanced micronuclear reactor developer in the world.
Okay.
They were looking for an advanced circuit breaker system with basically to significantly reduce the size, but maybe more importantly, reduce the amount of heat it generates. With those two things go hand in hand. So we bid into that contract against about 100 other bidders. There was three that were chosen. Don't know the names of the other two, but they were both wide band gap guys. And so the first three tasks were to go through design, prototype, and reliability testing. After those first three tasks, we were the only one left standing. And the main reason is, and actually this board, we'll be at PCIM this week, but and showing it, but this board is a 100 amp, 500 volt board. You can actually see it running 100 amps through it. There's virtually no temperature rise. Versus anything else, I should say. There is temperature rise, but it's
one of your
very low.
Core competencies, the ability, or features rather, the ability to sort of deliver that switching without any heat.
Right, exactly. So it goes. This is all Ohm's law, right? So the more the less efficient I'm able to transfer energy through that contact, the more waste heat I have. So I'm far more efficient, or we even call it ultra-conductivity over temperature. There's another aspect to this that's important. A semiconductor device, or silicon carbide, for example, is if I'm running power through it and it starts to heat up, guess what happens? The on resistant goes up, and then that causes more heat, and then it goes up. So you have to have a very elaborate thermal design in some of these things where we're constant over temperature, and so our thermal design is far more simpler and much lower cost.
Okay, and one of the things I think we talked about in the pre-discussion was around things like a Nest, which you evolved from. Well, not a Nest. I mean, where you have the sensing, and then you have something with the data, but then you have to actuate, and this is where it's useful for having switches like this.
So yes, so switches like this and all kinds of actuation things. So where we shine is distribution and control systems. Okay. So if I'm actuating lights, if I'm actuating an HVAC, that's probably further down the road. If in a circuit breaker system, I'm on most of the time and I'm routing power, not necessarily. I don't fit in a converter, for example. So silicon carbide and transistors or converters were distribution and control and safety.
Okay. Now, talking of which, manufacturing, scaling, at the moment, tell me about the manufacturing process, and then what are the challenges and how are you going to scale?
So one of the challenges of having a new material science means that the process doesn't exist in general manufacturing capabilities. So for example, a typical early stage semiconductor company is usually doing a new novel design and then going to TSMC or Global Foundries to have that built. We invented the process. We brought the process up in the foundry that we're in now, but it is it's a far lower cost process than a typical CMOS
you're
process. Talking
about 50 microns. So.
Our devices are cantilever beams that are 50 microns, and so we don't need fancy lithography, but we do have specialized chemistry to be able to do the material science, and so that's the scaling. That is the phase that we're in right now.
So you're currently doing it with a manufacturer in Sweden, Silex.
Yes.
Then you've committed some space in Ithaca, New York, to build and scale. So you'll need to raise money for that, I guess.
Yep, we will be building and scaling that as we grow, and so that part is started.
And what's next then?
What's next? Next is actually continuing this ramp that we're on. We're on a really heavy ramp right now. Things are going very strong, and the AI side. We're layering the first production of our aerospace and defense RF parts. Actually, we've gotten our first orders in, so that starts at the end of this year, so that layers on top. We're in the midst of the development cycle and partnering around this high power module business, and we expect to see that start to come to fruition in meaningful revenues in about 2 to 3 years. So that's how we expect to grow this thing.
Well, Russ, thank you very much.
All right.
Thank you.
Thank you, team. Appreciate it.